Good afternoon, everybody. Myself, Engineer H.S. Dhaliwal. Today, I am going to present a lecture on the magnetic measurements. First of all, what a magnet is. As we all know, that a magnet is a material or object which produces a magnetic field. This field is not visible, but it is responsible for the most notable property of magnet, that is called a force, which pulls on the other ferromagnetic materials such as iron, and it attracts or repels other magnets. So, a permanent magnet, it is an object made from a material that is magnetized and creates its own persistent magnetic field. So, this is the introduction of the magnet. As we can see, magnet, it has two poles, north and south poles. This is a horseshoe magnet having two poles of north and south. So, now we can say that the earth is a magnet. The whole earth, it is divided into the north pole and south pole, and the magnetic lines of force, they travel from north to south. So, this is the magnetic north pole and it is called true south pole, and the true north pole, it is called the magnetic south pole, and in the center, as we say in the equator, it is the polar axis. So, the magnetic lines of flux are there. So, we are having the geographic poles versus the magnetic poles. Lodestones are there, and the angle of declination. So, the very first compass, as we can see, if we are having a magnetite, that would be attracted towards north. So, this is called the first compass from where we can get the directions. So, now we are having the permanent magnets. So, the magnets that do not require any power or force to maintain their field, it is called the permanent magnets. One of the basic laws of the magnetism states that energy is required to create a magnetic field, but no energy is required to maintain a magnetic field. So, this is the definition of the permanent magnets. So, now we will start with the introduction. The magnetic fields and the electric current, they are closely connected to each other. As we all know that we are using the electrical motors, transformers, everything we are using with the use of electricity, they are concerned with the magnets. Magnetization and demagnetization takes place. So, similarly, the magnetic and electric fields, they are closely connected to each other. We can use the electric current flowing inside a motor coil to rotate the motor and convert this electricity into a mechanical power or mechanical rotation. But on the other hand, in the generator, we rotate a coil inside a magnetic field to create electricity and produce current that will flow from the generator coil. So, as we can see that the magnets and electric currents and the magnetic fields, they are having the very close relation to each other. When the electric current passes in the coils of the electric motor, then it will convert the mechanical electrical power into mechanical power, and on the other hand, if we put the mechanical power in the generator, then we will get electric current as output, that is due to the magnetism. So, magnetic measurements, it is the measurement of magnetic field strength in air, the determination of BH curve and hysteresis loop for soft ferromagnetic materials, and the determination of eddy current and hysteresis loss of soft ferromagnetic materials, and the testing of permanent magnets. So, as we can see again, the magnetic measurements, that the electrical and magnetic phenomena, they are closely associated with each other. The operating characteristics of electrical machines, apparatus and instruments are greatly influenced by the properties of the ferromagnetic materials for their construction. Therefore, the magnetic measurements and a thorough knowledge of the characteristics of magnetic materials is of utmost importance in designing and manufacturing of the electrical equipments. So, the knowledge of the characteristics of magnetic materials, it is very important while we have to design any electrical appliance such as machines, any apparatus or instruments, etc. So, now we are having the magnetic domains or molecules. First, we are shown the magnetic domains or the molecules of a ferromagnetic material which is not subjected to the magnetization, it is in the real state. Then if we magnetize the magnets, then it will be in this position, and this is the third position of the magnetic domains. So, now we are having the magnetic materials, the materials that can be magnetized, which are also the ones that are strongly attracted to a magnet, are called the ferromagnetic materials. These includes iron, nickel, cobalt, and some alloys of rare earth metals and some naturally occurring minerals such as lodestone. Although the ferromagnetic materials are the only ones attracted to a magnet strongly enough to be commonly considered magnetic material. So, in the magnetic materials, the three basic classifications are there. First is the ferromagnetic material. They are the materials or the metals which can be easily magnetized. They are known as the ferromagnetic materials. Iron, nickel, cobalt and manganese are the examples of the ferromagnetic materials. So, the ferromagnetic materials can be easily magnetized. Then we are having the second category, that is the paramagnetic materials. They are the metals that can be magnetized, but not as easily as the ferromagnetic materials can be magnetized. So, its examples are platinum, titanium and chromium. So, the paramagnetic materials which can be magnetized, but not as easily as the ferromagnetic materials can be. Then the third is the diamagnetic materials. The metals or the non-metallic materials that cannot be magnetized at any cost, they are called, the examples are copper, brass and antimony. So, the alloys often make the best permanent magnet materials. The combinations of such metals as aluminium, nickel, cobalt, copper and iron, they are commonly named as Alnico, AlNiCO5, are the commonly used in the production of the permanent magnets. So, the alloys which is made of these 5 metals, aluminium, nickel, cobalt, copper and iron, they are commonly used in the production of the permanent magnets. Then we are having the magnetic lines of force. As we know, the magnet, it has 2 poles, north and south poles, and the magnetic lines of force, they will travel from north to south. If we take the compass and draw the magnetic lines of force by using the compass, then we will get the magnetic lines of force like this. It is shown in this diagram, and again also it is shown in this diagram. So, the magnetic lines of force, they are called flux. Then the magnetic lines of flux repel each other and they never crosses each other. Then the lines of flux do not flow, but it is assumed that they run from the north to south. And one of the basic laws of the magnetism, that is the unlike poles attract each other and like poles repel each other. So, the basic law of the magnetism. Then we are having the demagnetizing, the disarrangement molecules in a magnetic material, that is called the demagnetization. So, in this diagram we are having the single phase AC stator winding. This is the current limiting resistor and this is the object to be demagnetized. So, this object can be demagnetized if we pass it through the stator winding of the motor. Then the other types that can be opted for demagnetizing the material, that objects can be demagnetized by striking. If we strike by hammer heavily on the object, then it can be demagnetized, and the objects can also be demagnetized by heating. If we heat the metals, if we heat the materials, then they can be demagnetized. Then we are having the different magnetic devices. We are having various types of magnetic devices which can be where we can use the magnets. So, we can use it in the electromagnets, we can use the magnets in the measuring instruments, we can use it in the inductors, we can use it in the transformers, motors, generators, alternators, and in the various applications. As we can see in the speaker, we are uses both a permanent magnet and an electromagnet we are using. Then we are having the magnetic field. What a magnetic field is? The magnetic flux density the density of the flux or the density of the magnetic lines of force. This is called the magnetic field, or also called magnetic B field, or just the magnetic field, and it is usually denoted by capital B. It is a vector field. The magnetic B field vector at a given point in the space can be specified by the two properties. First is its direction, which is along the orientation of a compass needle. So, the magnetic field can be specified by the two properties. First is the direction and second is the magnitude. In the direction, it is along the orientation of a compass needle. Second was its magnitude, or it is also known as the strength of the magnetic field, which is proportional to how strongly the compass needle orients along that direction, is known as the magnitude. And as we know, in the SI system international units, the strength of the magnetic B field is given in Tesla. So, the unit of magnetic field density, that is Teslas. Then we are having the magnetic moment. Magnetic moment are also called magnetic dipole moment, and usually it is denoted by Greek letter mu, is a vector that characterizes the magnet's overall magnetic properties. For a bar magnet, the direction of the magnetic moment points from the magnet's south pole to its north pole, and the magnitude relates to how strong and how far apart these poles are. In the system international units, the magnetic moment is specified in terms of amperes meter square. In the system international, the magnetic moment that is specified in amperes meter square. Then we are having the magnetization. This is the most important property of any metal. The magnetization of a magnetized material is the local value of its magnetic moment per unit volume, and it is usually denoted by a letter M, capital M, and having units of amperes per meter. It is a vector field rather than just a vector, because different areas in a magnet can be magnetized with different directions and strengths. Iron can have a magnetization of around a million amperes per meter, and such a large value explains why iron magnets are so effective at producing the magnetic fields. So, the magnetism, again, since the ancient times, certain materials called the magnets have been known to have the property of attracting the tiny pieces of metal. This attractive property is called the magnetism. As we can see we are having the two types of magnets. First is the bar magnet and second is the horseshoe magnet. Now we are having the electron theory of the magnetism. So what makes some materials such as iron, nickel or cobalt a natural magnetic material, or we can say the ferromagnetic materials? Why they exhibit the properties of the magnetic material? As we can say that the electron spin theory is there. Electrons becomes the tiny permanent magnets, and the electrons in the most materials spin in the opposite directions, and once paired they tend to cancel out any magnetic properties. As we can see in this molecular diagram we are having, these are the electrons, 2 and 8 electrons in the valence shell, and they are spinning. As we all know that the electrons spin throughout their axis, so these electrons become the tiny permanent magnets, and in these materials the most electrons spin in the opposite directions, and once these electrons are paired they will tend to cancel out any magnetic properties. So this is the reason why the ferromagnetic materials can be easily converted into the magnetic material. Then the electron theory of the magnetism for the what makes materials like iron different than the most materials. So its reason is that an atom of iron contains 26 electrons. 22 of the electrons are paired and cancel each other out, and the remaining 4 electrons located in the next to the outermost shell do not become paired and spin in the same direction, and these 4 electrons account for the magnetic properties of the iron. Then again, as the atoms combine to form the molecules, they arrange themselves to form a total of 8 valence electrons. In most materials, the electrons cancel each out. In the materials such as iron, the magnetic fields add rather than cancel. This additive effect forms regions in the molecular structure of the metal called the magnetic domains or the magnetic molecules, as we had seen in the last slides, the magnetic domains and the magnetic molecules. Then we are having the very important definitions. They are used in the magnetism in the concern of the magnets. First is the magnetic field. As we all know, the force field radiating from the north pole to the south pole of a magnet, that is called the magnetic field. Then we are having the magnetic flux, the lines of force between the north pole and south pole of a permanent magnet or the electromagnet. They are called the magnetic flux. Then we are having the hysteresis, a characteristic of a magnetic material whereby a change in the magnetism lags the application of the magnetic field intensity. It's known as the hysteresis. Then the retentivity, This is the ability of a material once it is magnetized to remain in the magnetized state without the presence of the magnetizing current. So, this is called the retentivity of the material. Then the permeability, it is a measure of a material's willingness to become magnetized. And the reluctance is a material's resistance to the magnetism. Then the saturation, it is a point when an increase in current fails to significantly increase the magnetic field. Then the residual magnetism, the amount of magnetism left once current flow has stopped, it is called the residual magnetism. Then Weber, it is the system international units of the magnetic flux, which represents 10 raised to power 8 lines. 1 Weber of flux is equal to the 10 raised to power 8 lines of the magnetic flux. So, these are the important definitions which are used in the magnetism. Then we are having the magnetic poles. The strength of a magnet, it is concentrated at the ends, which is called north and south poles of the magnet. Then a suspended magnet, if we suspend a magnet by tying it with a rope or a thread and we suspend it from any object and move it freely, then the north and south poles, they will be stayed in a particular direction, and also the compass, that would be north will attract the south and south will attract the north, because as we know the like poles repel each other and unlike poles attract each other. Then we are having the magnetic attraction or repulsion. These are the magnetic forces that the like poles repel each other. If we put the north and north poles towards each other, then they will repel each other. And if we are having the unlike poles, as we can see that the north will attract the south and south will attract the north. So, this is called the magnetic attraction and repulsion. Then we can again see the magnetic attraction and repulsion. If the like poles are brought together, the magnets will repel and the flux distribution will be as shown. As we can see, the flux distribution is here. These are the like poles, north and north, but they will repel each other and the magnetic lines of force would be arranged like this. And also if we put any soft iron or any glass piece, this is the diagram in which the soft iron piece and the glass piece is put over here. If a non-magnetic material such as glass or copper, it is placed in the flux paths surrounding a permanent magnet, there will be an almost unnoticeable change in the flux distribution, because as we can see, this is the glass put over here. The magnetic lines of force are not disturbed by any mean, but if we put a soft iron piece, any magnetized material, then the flux lines would be distorted like this. These are the magnetic lines of force traveling from north to south, but due to this iron piece, they are intended from its path. Then we are having the magnetic fields. So in the